Hi folks, welcome back. In this video I'm going to continue discussing patterns that we find in DNA. I'm going to continue showing how DNA cannot be explained scientifically. And in this video I'm going to look at the directionality that we find in DNA, which is denoted by the 5' and 3' positions in the nucleotides. But before I can do that, I have to explain what 5' and 3' mean. So to do that, let's take a look at this slide of our nucleotide once again. Here is the 2D image of a nucleotide that we've seen before. And this one would be A because it contains the base adenine. And what I need to explain is that the carbons in the ribose, they have numbers attached to them. And first of all, let me remind you, I've said this before, that there are carbons at the places where the lines indicating covalent bonds come together. As I said, they just don't draw them in, so it's assumed there's carbons there. And so what I'm talking about is there would be a carbon there, 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 and then there's that carbon. Okay? So all these carbon positions are given numbers. And those numbers are shown here. These are 5 carbon positions, the 5 carbon positions in ribose. They're numbered 1 to 5 as we go clockwise around the ribose ring, starting at about 2 o'clock. But they're also given a prime behind the number to distinguish them from the numbers that are used around the rings in the bases. So what we end up with, the numbers for the ribose, 1', 2', 3', 4', and 5' for each of the carbons in those positions. And let me just quickly show you the numbers on the bases since I mentioned that. Here we can see the numbers on the nitrogen and carbon positions around both rings of an adenine, A, and around a cysteine, C. I'm just not showing the ones on G and T. These numbers do not have primes after them, and we do that so we can tell the difference from the numbers around the ribose ring and the numbers around the bases. And I'm going to give you all this for free. This is actually going to be a bit of an upgrade for free tonight. I'm giving you a lot extra there. So I'm not going to charge you any extra for it. All right, but back to the prime numbers. Here we go again. The 2' position is important for the naming of DNA. Compared to a typical ribose sugar, which has an OH here, right here, would be an OH. In DNA, it's missing the O, right? It's missing an oxygen. So it's deoxygen at 2', or it's 2' deoxy. And that's what led to its name of deoxyribonucleic acid. That's another one. That's another upgrade today for free. I am just giving stuff away today again. So I guess it's your lucky day. And this is a good point to talk about another pattern from DNA. The DNA nucleotides, its building blocks, use the ribose sugar that's 2' deoxy. If you use the typical ribose sugar that I'm showing in this slide, which has the OH at that 2' position, that now becomes an RNA nucleotide, which are the building blocks of RNA, a different nucleic acid, which we'll talk about more when we talk about the functions of DNA. So, in DNA and its nucleotides, you only find 2' deoxyribose. So there's a DNA nucleotide, missing the O at 2'. There's the RNA nucleotide with the O at 2'. You see the difference there? DNA nucleotide, no O at 2', only an H. RNA nucleotide, an OH. And yet again, we have a pattern. Therefore, we have another element of design. We see a pattern in the sugars used in DNA and its nucleotides, and we see a pattern in the sugar used in RNA and its nucleotides. This structure tells us that intelligence and prescience are an absolute requirement for and during the design and creation of DNA and RNA, by the way. But like I said, we'll get to that later. You must know the structure of each nucleotide and which sugar to use ahead of time in order to plan to strategically, intelligently, and intentionally use them in the design and creation of the structure of DNA. Randomness, which is the basis of evolution, does not and could not create such a pattern of sugar usage in DNA and in RNA. Randomness, by definition, is the opposite of organization, logic, structure, order, choreography, and patterns. Randomness does not result from intelligence and prescience because it's random. Randomness is like repeatedly rolling a dice or repeatedly selecting a card from a deck of cards. There's no pattern to it because it always varies. You never know what you're going to get. There's no organization, structure, or pattern to it. It's like telling a programmer to create a program by randomly selecting the figures that he or she uses in creating the code. Since we know ahead of time that computer language is a binary code, if the developer was to just randomly select figures at their whim, you would never get a functional product. Randomness would result in the sugars being used in DNA and RNA in a random fashion. If randomness created DNA, there'd be a complete disarray of sugar usage, with each type being used in both DNA and RNA. Such a disarray would change the nature and composition of both DNA and RNA and destroy their abilities to do their life-essential functions. Other life-essential molecules would not recognize them as DNA and RNA. The fallout from this is that their functions would be lost and life itself would be lost. Life would not be possible. Therefore, randomness, which is the basis of evolution, does not have the ability to create such an organized, intelligent, logical, structured, and pattern in the usage of the sugars in molecules like DNA and RNA. And this leads me into an explanation of the directionality found in DNA. And I'm going to do this with my old friends here, the Legos. All right? Just like these Legos only go together in one direction, DNA nucleotides are the same way. So you can look at these Legos, put them together, right? Front to back, so to speak. That's the only way they'll go together, right? I got another one here. Let's use all of them. This is the only way they'll go together, right? You can try to do them front to front or back to back, whatever you call it, but they won't go together, will they? You can actually look at them. You can just look at them and see that they are designed to only go together in one direction. Well, DNA and its nucleotides are exactly the same way. So let me put those down and let me explain that for you. And once again in this slide, we have the prime positions in a DNA nucleotide. 1, 2, 3, 4, and 5 prime. When nucleotides get incorporated into a DNA molecule, they only go into DNA in one direction. And that direction is described using the 5' and 3' ribose positions. So that means this one and this one, right? Okay. When nucleotides are added into a DNA strand, they're added in what's called the 5' to 3' direction. That's because the enzyme that synthesizes DNA, called DNA polymerase, only works in the 5' to 3' direction. And we're going to talk about that more later when we get into the functions of DNA. It takes the 3' end of the previous nucleotide. Here are on the front, right, this guy there, and adds the 5' end of the next one to it, or the back, by binding it to the end of the phosphate group. And it's just like I was explaining when you add a front to a back with a Lego. Then when the DNA strand is completed, it looks like this, and we've used this slide before. And here you can see how the strand on the left is going down in the 5' to 3' direction, with the phosphate group in between there. So we're going from the 5' of this guy to the 3' of this guy, following that arrow that I have drawn there. But the fascinating thing about this is that the other DNA strand runs in the opposite direction. So while the 5' to 3' on the left strand goes down, on the right strand, it goes up. Each vertical backbone runs in the opposite direction of the other one, giving DNA its directionality. And DNA is read in the 5' to 3' direction of the alternating deoxyribose and phosphate groups in the backbone. The DNA bases are read and written in the order they appear in the 5' to 3' direction of the backbone. So when you look at the order of DNA bases along one strand, for example, let's just say it was T, G, C, C, G, A, T, T, A, T, etc., whatever they were, they're read and written in the order they appear in the 5' to 3' direction of the backbone. So on this slide, that means on the left going down, on the right going up. And that resulting order of the DNA bases is referred to as the DNA sequence. So on this short piece of DNA that I'm showing here, the DNA sequence of the left strand would be C, T, and then whatever would come next. But the DNA sequence on the right strand would be A, G, and then whatever comes next. They are read and written in opposite directions. And yet again, we find a critical pattern in the directionality of DNA. As I already explained, DNA must be opened up, have its information accessed from the bases in the middle, closed back up again, all without being damaged and remaining intact in order for the life essential functions of DNA to happen. This must happen as I described, or life cannot happen. And the several hundred molecules I told you about in previous videos that are involved in the life essential functions of DNA could not perform their functions if they could not recognize the directionality of DNA. They would never know where to start their job, which direction to go along, which strand. They would never know where to stop their job without the directionality of DNA. These other molecules rely on the directionality of DNA. So without the directionality of DNA, the ability of all these other molecules is lost, and therefore life is lost. Once again, this cannot be left to chance. And randomness, the hallmark of evolution, cannot account for this aspect of DNA. Therefore, you must know and understand this pattern ahead of time. You have to see and know the structure of DNA ahead of time before it's made, while you're still at the stage of making the nucleotides. Since DNA is constructed from individual building blocks of nucleotides that are attached together one at a time, the structure of the individual nucleotides must be strategically and intelligently planned to create and include directionality. Without the design of directionality in the nucleotides, the design of the directionality of the entire DNA molecule is simply not possible. And the fallout from that, life is simply not possible. So again, you have to know everything about the final product, the DNA structure, before you're making the building blocks, the nucleotides. And once again, you do not get such patterns from randomness. The directionality of DNA tells us that both intelligence and prescience are an absolute requirement for and during the creation of the nucleotides and the final structure, the DNA. Randomness, which is the hallmark of evolution, does not and could not create such an organized, logical, structured, choreographed, and essential pattern of directionality in the nucleotides and in the structure of DNA. Randomness, by definition, is the opposite of organization, structure, logic, choreography, and patterns. Randomness does not result from intelligence and prescience because it's random. So, how many times do you think I have to explain this before they'll listen? Well, here's the good news about that. I'm not tired. I can just keep doing this because I have a lot more to share with you. And we're going to keep doing that in the next video. And if you like what you hear, give me a thumbs up and subscribe to my channel. Thank you very much for watching. And as always, we'll leave the light on for you.